Hey kids, welcome to section 7.3 confidence intervals for proportions. Today you're going to learn how to find the confidence interval for a proportion and to determine the minimum sample size for finding a confidence interval for a proportion. So one of the most common types of confidence intervals is one that uses proportions. Many statistical studies involve finding a proportion of the population that has a certain characteristic. As with means, the statistician, you, given the sample proportion, tries to estimate the population proportion. So again, we're using a sample to estimate the population. Point and interval estimates for a population proportion can be made by using the sample proportion. So we still have point estimates. If we're trying to find a point estimate for P, which is the population proportion, we're going to use P hat, which is the sample proportion. On the basis of the three properties of a good estimator, P hat is unbiased, consistent, and relatively efficient. Unbiased meaning it is not going to be influenced by outliers. Consistent meaning that it's going to give you the same data time after time after time. And relatively efficient meaning it is the quickest way to get to the answer. But as with means, one is not able to decide how good of a point estimate P is. Therefore, statisticians, also use an interval estimate for the proportion, and they can assign a probability that the interval will contain the population proportion. So we have P, which is the population proportion. We have P hat, which is the sample proportion. And sometimes they'll give it to you and sometimes they won't. You can calculate the sample proportion P hat by taking X and dividing by N. X is the number of people in the sample who have a specific characteristic, and N is the total sample size. Just like getting P hat, we can find Q hat by subtracting from 1. So keep in mind that P hat and Q hat, if you add them together, equals 1. So we can never actually say what that P is going to be, but we can make an estimate. All right, so a random sample of 200 workers found that 128 drove to work alone. Find P hat and Q hat, where P hat is the proportion of workers who drove to work alone. All right, so we're trying to find our P hat and our Q hat. P hat is going to be X over N. And so the X is the number of drivers who drove to work alone, which is 128, over the total number in the sample, which is 200. If I divide this out, I get 0.64. Q hat is going to be 1 minus P hat. So you can do 1 minus 128 over 200. So that is 72 over 200, and that's 0.36. So sometimes your P hat and Q hat are going to need to be calculated. If need be, you want to go to 3 decimals. In this example, we did not have to round it all, so we were able to just leave our P hat, Q hat just the way they were. All right, so we need this because we're going to start making confidence intervals for a proportion. The rounding rule for a confidence interval for a proportion is 3 decimal places. And here is the formula for that confidence interval. I'll just shorten it for you. P hat plus or minus Z alpha over 2 times the square root of P hat Q hat over N. So we are taking P hat, which is our point estimate, which is our sample proportion. We're plussing and minusing or adding and subtracting. Our critical value, Z alpha over 2. Those Z alpha over 2s are the same ones from section 9.1. So we had 90% confident was 1.65. 95% confident was 1.96. 99% confident was 2.58. Those were the 3 most common ones. And then we have the square root of P hat, which is our point estimate, Q hat, which is 1 minus our P hat, divided by our sample size N. Notice that the value in the middle here is not mu anymore. That's because we are doing a confidence interval for a proportion, which is p. It does tell us that our n times p hat and our n times q hat should be greater than or equal to 5. So this should be greater than or equal to 5. This should be greater than or equal to 5. The reason why that's a condition is because we want to make sure that there's enough successes and failures to warrant there not being a writing down of the wrong information or having biased data to begin with. There are two assumptions for finding a confidence interval for a population proportion. One, the sample is a random sample. That's pretty much always going to be a here on non-negotiables that you always want to, if possible, have samples be random samples. And then two, we've got conditions for a binomial experiment are satisfied. The reason why we're talking about binomial experiments again is because our p hats and our q hats lend us to binomial distributions. You had to have two outcomes. You had to have a consistent probability of success. You had to have a fixed number of trials, and it had to be a randomly sampled. All right, so let's see how we can use some of these. Or how we can use a word problem to write a confidence interval. So, a survey conducted by Sallie Mae and a Gallup poll of 1,404 respondents found that 323 students paid for their education by student loans. Find the 90% confidence interval of the true proportion of students who paid for their education by student loans. All right, so a couple of things I need for the formula is p hat, q hat, n, and our critical value z alpha over 2. P hat is the probability of a success. In this situation, it's the probability who paid for their education with student loans. So that would be the 323 students out of 1,404. If I divide that, I get 0.230. Our Q hat is 1 minus our P hat. So 1 minus 323 over 1404. So that's 1,081 over 1404. And that's 0.770. Our n is our sample size. In this case, it's 1,404. Our critical value, 90%. 90% goes with 1.65. So our confidence interval p hat plus or minus our critical value z alpha over 2 times the square root of p hat times q hat over n. So this is going to be 0.230 plus or minus 1.65, get rid of that, times the square root of 0.230 times 0.770 all over 1,404. If I type this into my calculator and round to 3 decimals, I get 0.211 is less than p is less than 0.249. So basically, kids, what this is telling me is I took a sample of 1,404 people and found that 323 of them paid for their education by student loans. That turned out to be 23% rounded. So based on this sample of 1,404 people, in which 23% paid student loans, I can say all of these students who are in college, I can say with 90% confidence that the actual percentage is somewhere between 21.1% and 24.9%. So that's what we're going to write here. We are 90% confident that the true proportion of students who paid for their education by student loans is between 0.211 and 0.249. So we sampled this very small proportion of people, 1,404 students, and found 23% paid for their education using student loans. Based on that, we can say with 90% confidence that the proportion of all students who pay for their education with student loans is between 21.1% and 24.9%. Awesome. All right, here's another one. A survey of 1,898 adults with lawns conducted by Harris Interactive Poll found that 45% of the adults said that dandelions were the toughest weeds to control in their yards. Find the 95% confidence interval of the true proportion who said that dandelions were the toughest weeds to control in their yards. All right, so it looks like we surveyed 1,898 adults, and we found 45% that said dandelions were the toughest. So that 45% kids is your p hat. So they're already telling you what the sample proportion is. No need to calculate it like in the previous example. We can right away say that our q hat is 1 minus 0.45% or 0.55% or 0.55. We can also find our critical value z alpha over 2. It goes along with 95%, which is 1.96. All right, so our confidence interval p hat plus or minus z alpha over 2 square root p hat times q hat over n. We're going to have 0.45 plus or minus 1.96 times the square root of 0.45 times 0.55 all over 1,898. So if I use my calculator, I'm going to get 0.428 is less than p is less than 0.472. So this confidence interval explained is, it says with 95% confidence, we can say that the true population proportion of adults with yards who said dandelions were the toughest weeds to control is between 42.8% and 47.2%. So we sampled 1,898 people and got 45%. If I were to talk to the whole population, I'd get somewhere between 42.8% and 47.2%. So we are 95% confident that the true proportion of adults is between 0.428 and 0.472. So again, I'm not going to be able to say exactly what it is, but I can certainly estimate it with 95% confidence. All right, now what if we want to actually find a certain confidence level, but we don't know how many subjects to sample? Well, when finding minimum sample size, there are two situations to consider. First, if some approximation of p hat is known, like from a previous study, that value can be used in the formula. Second, if no approximation of p hat is known, you should use p hat equals 0.5. This value will give you a sample size sufficiently large to guarantee an accurate prediction, given the confidence level and the error of the estimate. So basically, if you're going to estimate how many people to sample for a future study, you either have old data to look back on or no data to look back on. If you have some old data from a previous study, that's what your p hat is. If you don't have any data from a previous study, then you're going to use p hat of 0.5. The reason for using that 0.5 is because when p hat and q hat are each 0.5, the product p hat q hat is at a maximum, which means that you'll get the the best results of trying to estimate what this population or this sample size should be. Using the maximum value yields the largest possible value of n for a given margin of error and for a given confidence interval. So basically, you're getting the best estimate if you have no idea what's happening previously. The disadvantage of this method is that it can lead to a larger sample size than necessary, so you might waste money interviewing people that you really don't need to in the first place. So here's our formula for minimum sample size n. We have p hat times q hat. Then we have z alpha over 2 over e, and we're going to square that. Notice that only the critical value divided by the error is squared. That answer is multiplied with p hat and q hat. Notice also that if necessary, we're going to round up to obtain a whole number. So if you do sample size and you get an answer of 10, perfect, move on. If you do sample size and you get an n of 10.4, you always round up to the next number, no matter what. In determining the sample size of the population is irrelevant. It doesn't matter if there's 100 people in the population or 1 million people in the population. The sample size is a minimum sample size and is no way dependent on how many people are actually in the population. Only the degree of confidence and the margin of error are necessary to make the determination. Notice, kids, in this formula, it does not matter what the size of the population is. All right, so here's an example. A researcher wishes to estimate with 95% confidence the proportion of people who own a home computer. The researcher wishes to be accurate within 2% of the true proportion. Part A says that a previous study shows that 40% of those interviewed had a computer at home. Find the minimum sample size necessary. Well, my formula for minimum sample size needs a p hat, needs a q hat, needs a z alpha over 2, and needs an error. In this situation, our p hat is our previous study, that's the 40%, which means that our q hat is 1 minus our p hat, or 1 minus 0.40, which gives us 0.60. Our z alpha over 2, our critical value, goes with 95% confidence, which is 1.96. Our error goes with how accurate we want to be. That 2% needs to be changed to a decimal, 0.02. Now I can find my minimum sample size, n equals, I'm taking p hat and q hat, and then I'm taking z alpha over 2, dividing it by the error and squaring. So here I'm going to get 0.40 times 0.60 times 1.96 divided by 0.02 squared. If I do all this and round appropriately, I get 2,305 people. So I would need to interview 2,305 people in order to be 95% confident that the true proportion is within 2%. That's my wiggle room on each side. All right, part B, assume that no previous study was done and find the minimum sample size. So no previous study was done means that our p hat is 0.5. That means our q hat is also 0.5. We have the same z alpha over 2, 1.96, and we have the same error, which is 0.02. So our sample size, p hat, q hat, z alpha over 2 over n, or over e squared. So I'm going to take 0.5 and multiply by 0.5 and multiply by 1.96 over 0.02 squared. If I do this, I get 2,401 people. Notice that my p hat, my sample proportion, went from 40% to 50%. And when I increased the probability or the proportion from a previous study, notice that my sample size increased. So if you're trying to come up with how many people you need to interview or subjects you need to sample, it's really important what a previous study was, or if you didn't have a previous study, because that will influence your calculations. All right, our application problem is all about contracting influenza or getting the flu. So to answer the questions, use the following table describing the percentage of people who reported contracting influenza by gender and race ethnicity. 49 states and the District of Columbia participated in the study. Weighted means were used. The sample size was 19,774. There were 12,774 women and 7,000 men. Explain what 95% CI means. So that's this heading over here. What does that mean? 95% CI means that you have created a confidence interval in which 95%, within 95% of the population can be found. So let's see, let's write that a little nicer. 95 CI means that these are 95% confidence intervals constructed from the data. How large is the margin of error for men reporting influenza? Well, if I look at men who are reporting influenza, here is the confidence interval. So to find the margin of error, I can find how wide the interval is and then divide by 2. So if I find the range of the confidence interval and divide by 2, this will tell me what the margin of error is. That's our error. So we're going to take the range. Well, the highest number is 50.5. The lowest number is 47.1. Subtract them and divide by 2. That's 3.4 over 2. So that means our margin of error is 1.7. That's 1.7%. What is the sample size? The sample size is right here, 19,774. 19,774 people. All right. How does the sample size affect the size of the confidence interval? Well, if you have a larger sample size, then your margin of error is going to be smaller and your confidence interval will also be smaller. So we'll put the larger the sample size, the smaller the margin of error, and the narrower the confidence interval. So if your sample size increases, then you are collecting more and more data to become more and more specific in your estimation. Well, when you become more and more specific, your margin of error decreases, which means your wiggle room on each side of the actual value decreases, which means your confidence interval narrows. Okay, number 5, what would the confidence intervals be larger or smaller for a 90% confidence interval using the same data? Well, a 90% confidence interval would be smaller than a 95% confidence interval since you are not having to include as many values. So a 90% confidence interval would be narrower than a we're using a 95% confidence interval. If your confidence level decreases, then your confidence interval width decreases. All right, final question. Where does the 51.5% influenza for women fit into its associated 95% confidence interval? Well, let's look at the women confidence interval. Here is the women right here. So where does the 51.5% fit in? Well, it looks like the 51.5 is right in the middle. If we are to add those together and divide, we would get the exact middle. So if we look at 50.2 and 52.8 minus 50.2 and divide by 2, then when you do this, you get 103 divided by 2, and that's where you get 51.5. So it is the middle of the interval. All right, kids, that is the end of section 7.3. If you guys have any questions, please let me know. And as always, keep calm and keep trucking.